Hey guys, we're going to start section 6.3, which is partial fractions. This is one of my favorite topics in Calculus BC. Okay, so it says in this section we show how to integrate any rational function by expressing it as a sum of simpler fractions called partial fractions. So I'm going to remind you of something we did in pre-calculus, and that was called finding a common denominator. So if I had asked you to find a common denominator for these two fractions, you would do something like this. You would multiply by the opposite denominator, and you would then distribute, add the numerators together, keep the denominator the same.
Mrs. Blosser, please call 2302. Mrs. Blosser, please call 2302.
Keep the denominator the same, and you would end up with something like 3x plus 3 over x plus 2 times x minus 1. Okay, here's what we're going to be doing today. We are going to be integrating things that look like this. But it's so complicated that it's not possible to integrate something that looks like this. So instead, we are going to backtrack all of this work to figure out what two simpler fractions added together would have equaled this thing. And we're going to set it up so that once we figure out what those two simpler fractions were, we're going to set it up so we can integrate each of those sums individually. It's quite a task. Here's kind of another example of what I'm saying. It's quite a task, but the process is very algebra heavy, not real calculus heavy. The calculus doesn't come in until you're ready to integrate. The algebra behind it can be lengthy and a little bit tricky at first, but this is something that is typically taught in pre-calculus, at least breaking down the partial fractions. So you guys are going to be just fine. All right. One thing we need to discuss, though, is that every time you see a fraction, it doesn't mean that you're going to have to do partial fractions. It depends on what kind of fraction or rational equation you're dealing with. So a rational equation is just one where there's a polynomial on top and a polynomial on bottom. If I have something called a proper fraction, that means that the degree on the top is smaller than the degree on the bottom. Okay, the degree of the top is smaller than the degree of the bottom. And if that is the case, it's possible to simplify that function. If the degree on the top is larger, then what you're dealing with is an improper fraction, where you would then do some long division, like we learned in pre-calculus, to simplify the function down. So let me show you what I mean. This example, the numerator has a higher degree than the denominator, so we're going to use long division to simplify this down. Okay, remember the ultimate goal is to be able to integrate it, but I can't do it the way that it is currently because it is too complicated. So we are going to use long division to actually figure out what x to the third plus x divided by x minus 1 would be. Notice I left a blank space here because I don't have any x squared terms. So I'm going to start with x times what is x to the third? That would be x squared, so that goes up here. And then I'm going to take x squared and multiply it through the x minus 1. So x squared times x would be x to the third. And x squared times negative 1 would be negative x squared. Okay, the next thing is to subtract those terms. You would have no x to the thirds and a positive x squared. Bring the next term down, which is an x, and repeat. So x times what is x squared? That would be x. Multiply x times x minus 1, so it would be x squared minus x. Subtract those two things, and you would get 2x. And then one more time, x times what is 2x? That would be 2. So we get 2x minus 2. Subtract. And you get a remainder of 2. Okay, now here's what you're going to do with all that. You are going to set it up, and you're going to say that the original problem of x cubed plus x over x minus 1 is equivalent to the quotient, which was x squared plus x plus 2 dx, because we're integrating, plus it had a remainder. So the remainder was 2, right? Well, when you have a remainder, that represents a piece of the whole that you were dividing by, and we were dividing by x minus 1. So we are going to write that the remainder would be over the divisor, which is x minus 1. Now I can integrate. I can integrate each of these terms individually, and I can integrate this fraction 2 over x minus 1 using ln. So my answer would be, let's see, this would be 1/3 x to the third plus 1/2 x squared plus 2x. And then we get to the fraction, that would be 2 ln of x minus 1 in absolute value signs plus c. So all of this is your first example for how to antiderive a rational function where the bigger degree is on the top. So this is using long division. Okay, next example is where we're going to get into partial fractions. So get ready. This is going to be a little bit challenging. So the first thing we're going to do is recognize that the top degree is smaller than the bottom. So you're going to have to use partial fractions. There's no way around it. Okay. First thing I want you to do is I want you to factor the denominator down as far as you can. So let's see. I think I can take out an x. I'm going to go up here and do this. I can take out an x. And I can factor this trinomial even further. That would be 2x minus 1 and x plus 2. So I've got it factored down. Okay, now, here is what I'm proposing. I am proposing that at one point in time, this giant rational function was simply the sum of 3 different fractions. One of the fractions had x in the denominator, because I see that as one of the components. One of the fractions had 2x minus 1 in the denominator, because that's also a component. And one had an x plus 2 in the denominator, because that was also a component. And we, combined like terms to make this whole big mess. The problem is, I don't know what the numerator was for each of these fractions, right? That's what we're trying to figure out. What would those numerators need to be to end up with x squared plus 2x minus 1, like is shown in this example? So we are going to figure that out. Here's what we're going to do. We're going to put A, B, C like I have here. And we are going to then kind of get a common denominator, if you will, for each of these fractions with the A's, B's, and C's still there. So if I were to ask you how to get a common denominator for this first fraction, you should be able to tell me that you would multiply by the other 2 denominators, right? You would multiply by the other 2 denominators to make this a common denominator. So that means we would be taking A and multiplying it by 2x minus 1 and by x plus 2. B, same thing. If I wanted a common denominator for this middle fraction, I would need to multiply by x and x plus 2. So let's write that down. B would be multiplied by x and x plus 2. And then C would have needed to be multiplied by x and 2x minus 1 to get a common denominator there. So C times x and 2x minus 1. Now, all of this common denominator work should end up equaling x squared plus 2x minus 1, because that's the numerator over here, and that's what we want to happen in the end. Okay, this is about to get very messy, because what you're going to do now is you're going to multiply all this stuff out with these a's, b's, and c's. So you can pause the video and try this on your own if you would like, but I am just simply doing algebra right now. So I'm multiplying all this stuff out. And I'm going to actually kind of keep the x's away from the a, b, c for the moment and just focus on multiplying everything through. Be very careful with negatives. Okay. Get this so we can see a little better. There we go. All right, here's where I'm at. So next thing, I'm going to distribute the A through the B and the C. So I kind of like to keep the letter in the front just so I can see it a little bit easier. So A 2x squared plus A 3x. I think you get the point. I know it looks really weird because we have so many unknown values, but we are almost to the point where we can find out what those are. Okay, so the next step is to take all of your like terms and put them in little groups, meaning this is an x squared term, here's an x squared term, here's an x squared term. So I'm going to write that with all three of them together in a group. And I'm going to continue to do that for all of my like terms. So next I'm going to put A 3x, B 2x, and then I have in my third group, oh, you know what? I made a mistake up here. This should be an x. Ooh, that was close. Okay, let me fix this. So minus C2x, there we go. And then I have just this A2 here. That's the only, like, I guess, constant term. So that'll go on its own. Okay, now look, all of my terms are now grouped together, so that means that I have something in common in this first group. So I'm going to factor out what they have in common, which is an x squared. That leaves me with, actually I'm going to write it as 2a now. So 2a plus b plus 2c. And I'm going to take out an x from the middle group, which would be 3a plus 2b minus the c or 2c. Oh my goodness, I just found another mistake. It's just c. You guys are probably at home like, hey, Strope, get it together. I will get this. Okay, that was a 1 x. This should be cx 2cx. No 2. Just CX. Okay. Goodness. There. Okay, and then I still have this minus 2a thing going on over here that I can't do anything with yet. All right, that was a lot of algebra. Now, here's the important connection I need you to make. Do you see how this is an x squared out here, and we also have an x squared over here on this side of the equation? I am going to use that, and I'm going to say that the coefficient on this right side in front of the x squared is a 1. That's what I need the coefficient to equal for the x squared, because that's what's given in the problem. All of this stuff in parentheses represents what the coefficient needs to add up to. The coefficient needs to add up to 1 because that's what the problem is set up as. So I'm going to say this. I'm going to say 2a plus b plus 2c has to equal 1 based on the way the problem is set up, because it's 1x squared value. The same thing goes for the next part. I have a 2 in front of my x term, which means that all of this stuff in front of the x needs to equal 2. So I have 3a plus 2b minus c has to equal 2 per the way the problem is set up. And then the last thing is that this negative 2a is my constant value, and it has to equal negative 1. So I have a third equation where 2a has to equal negative 1. I'm going to end up with 2 or 3 equations depending on how complex the problem is. I'm going to solve whichever one is the simplest to solve. So that would be this third option. And that gives me a is equal to 1/2. So right there you have, star it, you have one of your coefficients from the original problem. So that means this coefficient a is a 1/2, which is great, very helpful, but we need to keep going to find all these values. So we're going to go through and we're going to plug in 1/2 for these a's up here. So we're going to end up with, let's see, if I simplify, this would be, I'll go down here, b plus c, 2c, b plus 2c is equal to, what would that be, 0? Okay, I'm going to plug in 1/2 for the second equation, the one in red. And I'm going to solve, and I would get 2b minus c is equal to 1/2. 2 minus 3, yeah, 1/2. All right, now I've taken an equation with 3 unknowns, and now I only have 2 of them. So from here, you can either do elimination to solve the system, or you can set up a substitution problem, which is probably what I'm going to do. I'm going to go over here and I'm going to solve for b and say b is equal to negative 2c, and I'm going to sub that in to the problem. And I'm going to solve. So this would be negative 4c minus c equals a 1/2, and that would be negative 5c equals 1/2. And if I solve, I would get c is equal to negative 1/10. Okay, that's another one of my unknown values that I needed. The last thing I have to do is go back and use that to find my value for b, which b up here is equal to negative 2 times c, which is negative 1/10. Therefore, b is equal to 1/5. Okay, look, all of this work is nuts, but all of this work is there to help us set up an integral that we can actually integrate. So we are not done, okay? We're going to go back. We're going to go back to this area up here at the top where we had a over x, b over all this stuff, and we're going to plug in the A, B, and C values that we just found. So let's get some room. I'm going to go back and reemphasize the whole main goal. The main goal was to be able to integrate this very complicated fraction. Okay? And we said that we could do something equivalent by breaking it into partial fractions. And this is how we had it set up in the original problem, at the beginning of the problem. And so now we're going to plug in those A, B, and C values. So we said that C was equal to -1/10. B is equal to 1/5. And A is equal to 1/2. Okay? So we're going to say that this would be equal to, you know what we could do to make it easier is put those constant values in the front since we're integrating. So we could say 1/2 integrate 1/x dx plus 1/5 was the b value, and that was for 1/2x minus 1 dx plus, whoops, minus, it was -1/10 minus 1/10, and that was for the fraction 1/x plus 2. So I'm just kind of rewriting and pulling the constants out to make it easier. You are to the final step. The final step is to integrate. This first integral has a 1/2 in front, but the antiderivative of 1/x is ln. So this would be 1/2 ln absolute value x. And in fact, all of these are kind of versions of ln because they're all linear functions in the denominator. Just don't forget your absolute value. And we finally have an answer.